Alrighty, guys. Holy cow. Today we're going to get past the little bit of a bump that we're on. Is that better? Okay, so we're going to go through and review the function representation of revolute joints. Then we're going to go through and introduce the function representation of a general transform using a DH, the DH parameters. We will not be going through and using this one per se. You could if you wanted to, but the fact is we will only be considering revolute transformations in our MATLAB model. After we get done with that, we'll take a look at how we can use MATLAB to display the positions of the joints and the end effector, because ultimately that's what we're after, is making sure we know where everything in that robotic system is. And that's kind of what distinguishes this class from the 277 class. In 277, you guys are just interested in getting the Lego robots to do things. Here, we're actually interested in making sure that we can move a manipulator repeatedly and track its position and accurately model its motion. Okay, and then finally, if we have time, I'm going to introduce you to the basic components in our numerical methods for inverse kinematics. As I was mentioning before the class, what this comes down to is doing nothing more than taking a look at the position of the end effector and the position of the destination and trying to minimize the distance between those two locations. Ultimately, if you just find the distance between a destination and the current position and then adjust the joint to make it smaller, then you're moving in the right direction. So we will take a look at that real quick. So, real quick, let's go back in and review the function representation. And I'm going to, do you guys want to just see it up on MATLAB, or do you want to have me write it out? If I open it up on MATLAB, I can have it up here. You guys, I can go through and explain it while you guys are typing it into MATLAB. Keep in mind that that is essentially problem number 1 on the homework for you. It'd be nicer if you had MATLAB. Okay, so I'll do that. I mean, that just makes a lot more sense. Okay, so
Are we doing the alpha radius theta arms 1, 2, and 3?
Yep.
Okay.
And ultimately, you can set it up any way you want, but however you set it up, you have to make sure that your you implement your function appropriately. So wait for it to come up here real quick. Typically, when you see these DH parameters listed, you see them listed as alpha, I'm sorry, I'll call this the joint, or the link twist, followed by the link length, followed by the joint offset, followed by the joint angle. Okay. In this case, we're not including the joint offset here just because we're not considering prismatic joints. So with that being 0, then we're just going to go through and pass in our alpha, our joint twist, or our link twist angle, our radius, and our theta. If you do go through and list those in a different order, just make sure you keep track of it, because ultimately that's the order in which you'll have to pass information into your function so that the function can do its job appropriately. Okay. Notice that what I did on my example I did over the weekend, which for some reason I did not remember doing this, is I passed in one vector parameter. Now yesterday I was trying to format that as a vector that was coming into MATLAB, and that's where the problem was. By passing in a parameter that is a vector, that's an entirely different thing than trying to pass in a bunch of discrete data and formatting it as a vector. So when you pass information into these functions, make sure that you're passing them in as discrete values or discrete variables. They can be vectorized parameters or even matrices if you want, but you cannot have those expressed as a vector or a matrix as I had yesterday. Also notice that, unlike my advice yesterday, I have a rather obnoxious function name, so I'm going to have to carry that around with me as I'm using this. And then I go through and assign my first parameter to alpha, my second parameter to the radius, and my third parameter and that parameter vector to my theta. And then I send the calculated matrix back. Okay. All I'm doing is going through and saying that the value that I'm returning, which is out, if you look up there in the function definition, the value I'm returning is out, and out is equal to the homogeneous transformation here as we developed in class. So that makes sense? So how many of you have already got this down? A couple of you. Okay, so what would we do then if we wanted to make this a generalized transformation? Do you guys need a minute or so, or?
I think I have it.
Okay. Okay, so what would we do then if we wanted to make this a general transformation? That is, a transformation that's able to handle both rotations and translations.
What if we add another line?
Well, we wouldn't add another line, but we would definitely add in that fourth parameter to our input.
That's what I'm getting at.
So if we wanted to change this so that it was a general transformation, we first off want to change its name. And we change the parameters that we're passing in, link, offset, and make sure that I'm keeping the variables expressed correctly. Is going to equal parms sub 3. Okay, so now we're passing in the information properly. Notice that now, since my function name does not match the file name, that it's giving us an error. Whenever you're writing a function, the file name has to match the function name. If it does not, you will flag an error there. So I'll save this as general transformation. Okay, and now that error check is not flagging the name as a problem now. Okay, the only other thing that we need to do then, let's see, why is it causing, saying that that's a problem? Oh, so here it's flagging this link offset as a problem, not that it is, but because it's not used anywhere. So anytime you have a variable assigned that's not used subsequently, it'll tell you that just by putting the squiggle up underneath it. That makes sense? Yeah.
This function is only for rotations about the y-axis.
No, in this, the revolute function will perform, the revolute transformation function will perform either a rotation about x, a rotation about z, or both, okay? In order to perform a rotation about y, we have to trick it by doing a two compound transformations back to back like we were talking about yesterday.
Mm-hmm.
That makes sense?
Yeah, I'm just trying to figure out what the, before when we had rotations about a certain axis, we had, you know, a matrix and we'd have ones and
Right.
zeros and cosines in certain
Well,
places.
the entire thing, reason why we don't have the rotation about y set up is because when what Dinavet and Hardenberg, when they were initially setting up these parameters, they were trying to come up with a minimum set of parameters. And in order to define the minimum set, if you think about it, if you're firing like a artillery piece, you don't need to know anything about the y-axis. You just need to rotate and elevate in order to get the job done. And that's kind of the same idea that's going on within this robot. If we rotate around an axis and then elevate off that axis, we can achieve any orientation we want, okay? Now, in the case of a rotation about y, like we ran into, then we have to trick it by performing a 90-degree rotation about x, a 90-degree rotation about y, about z, and then doing a subsequent rotation about x again to get everything straightened
I
out.
mean, we could still get that done with this function, we just
Yeah,
call it
absolutely.
3 times or whatever.
Right, so then you just have to do a static, you'd have to send a static set of DH parameters in, followed by a subsequent set that would actually perform the rotation about y.
So that output matrix is set for any rotation we need to achieve that. So
Exactly, and that's the beautiful thing about this, is that the Revolute transformation that we just got done doing will work for all of our transformations that we'll be doing in here. And that's perfect. I mean, that's what we want to do, so. Okay, so if we're incorporating the link offset, then if you remember, the only thing that changes in our matrix here is we now have a x and y, a y and z component as well. And this becomes then our link offset, well, negative link. And watch this, as soon as I type this in, our link offset up above will become happy again. Times sine d of alpha. Okay, and now link offset is being used, so it's happy, or as happy as it can possibly get. Times cosine key of alpha, and I suppose I can get rid of that. Okay, and now we have this matrix set up for a general transformation. Now, the only thing that we'd have to keep in mind is when using this general transformation, we'd have to be passing in 4 pieces of information at a time rather than just the 3 that we were previously. However, if you did want to be able to model these link offsets or model the motion that we have on the Atlas II robot here, where we have this prismatic joint, then we would have to use this general transformation rather than the transformation that we were using previously. Good there? For all of our modeling, we'll be using the Revolute transformation rather than this one. But if you want to get really creative and technically use the right transformation, this would be the one that gets everything done for us rather than just the simplified models we'll be doing. Part of the reason for that is because we've only got, what, 3 weeks and a day left, and tomorrow is a work day, so. Okay, so any questions here? So now that we have these put together, what we can do is, I'll save this just so that I have it. But I could come down here and I could do Revolute transform, it's a capital. And pass in a set of parameters. In this case, we are, oh, and notice this, it actually pops up with your help file there too. So just like any other function, now This function is part of your help menu, so it'll list your intended parameters that you pass into it. So in this case, if we wanted to calculate a 45-degree rotation about X, followed by a link offset, a link length of 20 units, followed by a frame rotation of 25 degrees, or 25 degrees, that would have actually caused an error for us because I need to format this as a column vector. So 45 colon, what did I say, 20 centimeters for the length,
And then 25.
then 25 degrees for the frame rotation. It'll go through and specify the rotation, or I'm sorry, the homogeneous transformation that would get that done. Yes?
I'm getting in there,
Uh-oh.
getting tight couple.
No.
Is it connected to your N drive or where?
Oh, yeah. Yeah, so don't forget that when you save your function, your directory has to be pointing at the same location. So send it over there to him, and then put it under the robotics folder, and then you should be able to, okay, now, go ahead and just take your up arrow, and there you go. Yeah, so don't forget that you have to change the path in order for this to work. So if you'll notice, all of my scripts are done, scripts and functions are saved in the yeah, I click away. Yeah, I know. Didn't it work? They are saved in the N drive, under the current year, under the term, 477, and then MATLAB examples. And if I try to execute this without that path being set, then it'll cause problems. Okay. So just keep that in mind. You have to have your path set before you try to execute this. The reason it probably worked this time is because I had already pointed at that path one time previously, so that makes sense. Okay, now let's step it up just a little bit. Let's say that we want to determine or model the, I suppose I should have just written this down over here. But let's say that we want to model a robot with the following characteristics. We want to say that our joint twist angles and our radiuses and our joint angles are defined by this array, so 0 degrees, 0 in length, and 30 degree rotation, followed by 90 degrees, 0, and 45 degrees. Then we'd have 45 degrees, 20, and negative 60 degrees, 45, 20. I'll go ahead and talk about these here in just a second. And then finally 10, 0, 10, and 0. Okay, so what's this string of parameters doing for us? And by the way, this would be our harms. that we would define. We wouldn't necessarily set it up as an array like we have here. We could if we wanted. We'd probably just call this arms and then tell it when we're accessing our MATLAB file to send a particular column to that function we just created. For example, if we have this defined as we do here, I'd probably go through and say, well, if I want to model the third transformation, I'm going to pass harms the all rows, because I want to include the information in all three rows, so I put a colon, comma, the third column. And that would go through and calculate the transformation associated with that third set of parameters, okay? Now, geometrically, what is this first transformation doing?
Like 30 degrees on the z-axis.
It's rotating 30 degrees about the z-axis. Good. So we know that we're rotating 30 degrees about the z, so we're projecting or rotating our frame 30 degrees about the z, so everything that we do is going to be projecting out in this direction. Okay? What's the next one doing then?
Doing the same thing, 45.
It's almost doing the same thing, but what's it doing first?
You gotta rotate 90 degrees about x.
We rotate 90 degrees about x, so we're going to take this frame here, which is our new x prime. We're going to rotate 90 degrees about it, so this will be our new z prime. And then this will be our new y prime. Okay, after we do that 90-degree rotation, then we're going to elevate 45 degrees off of the horizontal axis, because now our z is the axis that we're rotating around. So we're going to rotate 45 degrees off of that axis, and this becomes very difficult to see, but we have a 45-degree angle projecting that arm off of the horizontal axis. That makes sense?
Isn't our y moving too at that point?
In this case, we would, since we're, let's see, rotating about x and then rotating around z.
So y and x would move
Right.
45 degrees.
So what we'd be doing is our frame would be looking something, that's a little better. So this would be our new y double prime, and this would be our new x double prime, and right there would be our 45-degree angle. And it would just be rotating off of the existing x by 45 degrees. Okay? And then as we do each of the subsequent transformations here, we would be applying the each of these transformations accordingly. They're going to get kind of cumbersome from here, because now I'm doing a 45-degree rotation rather than this orthogonal rotation. And from there, we'll just let MATLAB do the rest of the work for us. What do you kind of notice about this? We're probably going to use the identical method that we've already developed for setting up these models. Previously, what we have done is we've gone through and assigned a number of frames. Okay. So this is going to be kind of small because I'll go ahead and zoom in on it, but I'll have to do a bunch of moving around. Would you guys prefer to have it zoomed in and then watch me frantically try to scroll around on the screen, or leave it zoomed out so I can talk about the entire page?
This is large enough for me.
Okay.
Right?
So I'll go with this then. Okay, so if you recall, what we have done up until now when we're drawing these frame descriptions is we have gone through and we've defined our base frame. This is just our IJK axis oriented in, at the origin. Then what we have done is in defining frame B, we've taken the transformation that we were working with times that frame A. That moves and rotates and does whatever else we need it to do to that frame. When we did a subsequent frame calculation, we then go through and do the first transformation times the second transformation times the frame. The third frame, we go through and do the first transformation times the second transformation times the third transformation times the original frame. And we do this each and every time. The nice thing about this is it is using the exact same process that we've already used. The only thing different now is we have a more compact way of representing each of these transformations. Because we have this standardized function that we've set up so that we don't have to type out these big long transformations manually. Okay? So this is the exact same method that I've already used in setting up our frame representations. We're just now going to recognize that these transformations truly represent the links and their orientations on the robot. That makes sense? So I'll give you guys a minute to go through here. If you have your homework set up, if you take a look at, what was it, problem 9 from last week's homework? Or maybe it was 10. 9?
10 was the coding part, 9 was just.
Yeah, it was the last coding, or the second last coding problem that you did, so.
Can you go
it was
up a little bit?
Sure.
Your lines better.
So the only thing I did to start off was I just told it to hold the axis on. That just makes sure that you retain the same information on the screen as you do subsequent plots. If you don't have that hold on, what will ultimately happen is it'll draw one vector and then clear the screen and draw the next vector and so on and so forth. That makes sense? The axis and the view, what I do in defining the axis is I pretty much take the sum of my lengths and establish that as my min and max, because that represents the workspace that we have available to us, in fact, the maximum workspace. If we, in this case, I know that this particular configuration is going to be isolated in the first quadrant, so, well, the first octant, I should say. So I haven't gone in a negative direction, but in the case where you're expecting to do full 360-degree rotation in a spherical workspace, you would want to make sure that you go through and you'd want to make sure that you go through and set your axis to -50 to +50, -50 to +50, and so on and so forth, because the sum of our lengths is 50 in this case. Good?
For what, our axis, you said?
Yeah,
You do -50 and 50, so.
yeah. And that's only because that's the maximum reach of our arm configuration. Okay? And then with that then, we have our joint angles. These are going to be the joint angles that actually vary once we start manipulating the robot. And once we do that, then we'll go through and set up some kind of controlled structure in here to alter those joint parameters in order to determine the configuration of the robot. Good? Okay, now one thing that you guys could do along the same lines as what we've already done, is you could probably set up a function to perform these calculations for you. You could go through and set up that function so that you pass in your DH parameters, you call this Revolute transformation repeatedly in order to calculate the transformation for whichever frame you're looking at, and then you return the transform matrix given that information, okay? Not saying you have to do that. In fact, this is the approach I will use throughout the rest of the quarter just because it's the approach I've already started using. I don't tend to like to change directions in the middle of strings, so. Okay. After we do that, we know from our previous work that the next thing we do is we go out and we plot, just like we've been doing. We go through and plot the X, Y, and Z of our first frame, the X, Y, and Z of our second frame. In this case, I'm not bothering to change the color because at this point, we're only interested in being able to see essentially where the Z-axis is, to make sure that that's the axis we're rotating around. And with that being said then, once we have that plotted, then we can go through and plot each of the, it's not scrolling down, there we go. This region here, sorry, this region here is what actually plots the links of that robot in the particular configuration, okay? This is all identical to what I used in the first two homework assignments in order to get the different frame representations plotted. Pretty slick, right? I mean, early on it didn't really have any real merit to us or anything, but now it's all hopefully coming together as to why we put it, put things together the way we did. The line width, notice I do something kind of irritating. I set the line width at 7, 6, 5, 4, and 4. That's only so that I can distinguish the base, the links nearer the base from the links that are further out on the chain, okay? You don't have to do that. One of the problems with doing this is that these are only drawn two-dimensionally. That means if you do a rotation about this line that has line width of 7, well, you'll see a big fat line from the perspective facing you, and as you rotate it, it'll just become a one-dimensional object again. So you can do that if you like. I do it just to help me interpret the representation a little bit more. You'll also notice that since our first two rotations were about the or first two transformations were about the origin, the first two vectors here aren't going to do anything but reorientate the frame. Okay. So once we run this, we see that this is the configuration that we would have for this particular set of DH parameters. Now, what do you notice here? One of the problems specifically asks you for on the homework to state and determine where the position of each joint is located. And the end effector. The end effector is ultimately what we're trying to keep track of, because that end effector is what's doing the work for us. How are we going to go in and determine the locations of each of the joints and of the end effector?
Can't you get it to just spit out the numbers separately?
Yeah, that's exactly it. We've gone through and we've calculated frame A, frame B, frame C, frame D, frame E, and frame F. Guess what? The last column in each of those matrices represents the X, Y, and Z coordinates of the joint that you're working in. So if you want to go in and, let's see, I need to that's not it. There it is. So if you want to go in and determine the position of the end effector, you can just go through and say, well, I want to look at frame F, because that represents the end of the end effector, and I'm going to look at elements. Let's see, that would be 6 columns, 4 rows, so I want to look in rows 1 through 3, because we want to look at the X, Y, and Z, and then the 6th column. And there is the position of the end effector.
Is that good for all of them?
If you want to look at the position of the first joint or second joint or third joint, then you just go through and pick out the particular frame that that joint is located in and do the same thing. For example, we know that frame B and frame C are still centered at the origin, right? So with that being said, we should see that frame B, 1 through 3, comma 6, is 0, 0, 1. Why is it 0, 0, 1? Let's see. Am I doing that right? It would be 1, 2, 3, 4, 5, 6. No, actually, it would be the, okay, it would be the 5th column, wouldn't it? Because that represents the starting position of each of those. Good. And is that even right? Let me, okay, I'm sorry, I'm incorrect. It would actually be in the first column of each of the respective frames, because that represents the X, Y, and Z of our origin. Okay. So, now, one thing that we can do with this is we can actually introduce that into our plot itself. And we introduce that by using the text command. So if we go through and state that we want to introduce text, we have to first tell it where we want to position that text. In our case, I'm going to position it at 0, 0, -10, meaning that I'm putting it right below the origin on the below the XY plane. Okay, and then what I'm going to do is just see where it shows up here and run the text. Okay, so you can see that it's showing up where I'm intending it to, but it's not necessarily real nicely formatted. So what you can do in order to make sure that it's centered at that location is you can use the horizontal function and say center. And I might have to look at this command. Yeah. So it is you'll find that some of these arguments are hard to remember, so now the text string that we have there is centered. Now, in order to get it to display the location of the end effector like we want, what we would end up having to do is give it or convert each of the numeric values to strings and then display them. In order to display a series of text strings together as one element, you have to include them in an array. So, let me zoom in on this real quick and I'll show you how to do this. Okay, so in place of the text field, we introduced a array, and first thing we want to do is include a left bracket, so I'm going to put that in parentheses. And then we want to include the first coordinate of the end effector position, which we're going to have to do a num to string command, so num to string. And we're going to use information out of frame F, so F, and we know that that's in position 1, 1. And then we're going to go in and put a comma to separate that from the next. Row 2, 1 is the origin of the next position. And then another text comma to separate it, and followed by num to string. When we were in C, did we ever do numeric to character conversions?
I think so.
I thought we did. I mean, C has almost identical functionality. You can do conversions between numeric to character and character to numeric and whatever else, so. 3, 1. And at that point, we're done. Oh, no, we're not. We need to close the parentheses, and now we're done. So now when I should stop moving around like mad. Your parents buy you booster seats and stuff. Sorry. So,
I did have a boss that bought me a step stool just for me. He thought it was a joke and I actually used it.
you know, I tend to be very utilitarian minded, and if something has a use, even if it's,
I know we use it.
yeah, even if it amuses others, I make use of it. Good. So let's see if I actually did this correctly.
Isn't that gonna error where your red line is underneath that?
Yeah, it probably will, so let's see, right, so what's the issue here? Okay, so go back to the command window, and it says bracket issue, so I've got okay, so on one of, yep, it's right there. So that should take care of it. Okay, so where's the problem now? It's there. It's not brain, no, please. There we go. Okay, so now we have the position of the end effector listed on the plot. So let me, there you go. That way you can. Now, what you'll see is, next thing we're going to do is look at varying one of the parameters like we've done a couple times already. This will set you up for the final part of the assignment for this next week. I'm not going to go through and demonstrate how to vary multiple parameters. You can probably figure that out on your own. But one of the issues you have is if you do include a text string on your plot, by drawing that series or redrawing that series of plots, you're going to constantly be rewriting over your existing character string. So I believe I have thought through a way of overcoming that issue, but we'll see when we start plotting this. Okay, everyone have the text. Okay. So this is only if you want to include the text locations. Technically, if you wanted to, let me run this again. And why did it do that? Okay, so technically, instead of listing just the input, the position of the end effector here, you could go through and list the position of each of the joints, you know, right in close proximity to those joints. So you could go through and say, okay, well, this is 0, 0, 0, obviously. This is whatever the heck it is. That joint's whatever it is. And then this end effector position, you could list up there near where the end effector is actually occurring. Okay? And it would be the exact same setup, or exact same setup for your text string. You'd just be pulling different data out. You'd be pulling data out of your frame A and whatever frame is going on here or is being used here and so on and so forth. Okay. If you do that, because we're working in a three-dimensional environment, you'll have to play around with the positioning a bit because it'll be kind of tricky. This is going to draw it based on the X, Y, and Z coordinates that you give it. Okay? The text will not be scaled with respect to everything else in your, I mean, if you place it far away, it's still going to be in the same relative font size as it is in this position. So really all you have to do when you're positioning this text is find your X, Y, and set it at 0 relative to that location, and it'll show up right here. So if you have, say you want to go through and place it at 30, 15, well, that's not real good, 30, 20, that would place it at this position, which isn't too bad. So 30, 20, 0 would place the text for this joint at this location, and that would be pretty dang close. You could go through and try to play around with the z-axis as well, but if you do that, it's going to really become kind of confusing. Now, keep in mind that that placement will be relative to the orientation you're using. As soon as you try to grab it and rotate it, I'll demonstrate with this text here. Okay, as soon as I rotate the image, look at what happens to that text. It stays in that same relative position, but now that my frame is moving, the text is becoming, you know, less usefully placed. Good? So keep that in mind. If you place your text in one relative orientation and then move the image, the placement of the text is going to change its relative orientation as well. Good? Alrighty, so let's quickly, since we have 20 minutes left, but let's quickly talk about how we can set this up to move a joint. What I'm going to do here is I'm going to use, instead of a for structure as I did yesterday, I'm going to use a while structure. And the nice thing about using a while structure is then you can use the existing parameters without having to initialize those parameters, okay? So what I'm going to do is, let's say that we want to look at the motion when we rotate our theta 1 about the z-axis. Okay, so as we rotate this about the z-axis, we're going to rotate it from maybe 30 degrees up to 120 degrees. So if we want to go through and perform this rotation, I'm going to go in and say that while theta 1, which is in location, is in DH arms, let's see, it's in row 3, comma 1, row 3, column 1, is less than or equal to 120 degrees, do the stuff that follows. Okay? And after I get done with this, I'm going to make sure that I say that the information in that position is updated. Did you have a question?
No.
Okay. So I'm going to say that DH parameters is equal, I'll put this up top again. Is equal to DH parameters plus 1. I'm doing this because we're moving in the positive direction. If we're going from 30 to 120, then we're moving in the positive direction. And at that point, I can end. So I'll screw up just to show you the formatting for the while loop. The while loop is formatted exactly like it is in C. The only difference is you don't have to include the curly brackets before or after. Everything between the function, in this case the while function, and the end is considered to be within that while loop. Okay, so, did you get that part? Okay, so now that we've got that, if we run it, we see that we run into the plot that we're expecting. Now this is not an animation, okay? This represents the original position and the final position, but we don't see the motion itself. If we want to include the motion, or actually be able to see the motion, what we can do is within each loop we can tell it to draw now. Okay? And what that'll do is at that point, everything that's in the draw buffer will be displayed at that point. The next time through, it'll update the display buffer over and over again. So now if we draw it, we can see the actual motion taking place. And so we have our animation of the motion within this robot configuration. Make sense? You can see that my window isn't real conducive right now to rotation, so I'll go ahead and update it. Okay, notice what is happening here as well. What is this black thing
Your
here?
text.
That's my text. And because it is not being, since it is retaining the information from previous plot, eventually it gets to just a big old blackout section of the screen. So I think, and we'll play around with this for just a second before we run out of time today, that if we go through and do something clever like this, where we put a hold on at the beginning of the loop, and then a hold off at the end of the loop. Actually, I think this will have an adverse effect. It'll still be cool because I think it'll clear the previous drawing. So you'll actually be seeing the motion itself rather than each of the previous motions. No, that did nothing, so let's try that again. So let's go. Let me see if there's a clear. Yeah, I should have done it. Okay, there we go. So what I did was I used a clear access command here at the end. And when I did so, what this did for us is allowed us to view the motion as a true translation. And I think what we ought to do is probably put that near the top. That way it clears it before we enter the loop instead of after. There we go. So it retains that position. Now, just for the heck of it, let's do the same thing. And I'm going to be really sloppy here in my programming, but who cares? I'm going to just copy this entire thing. And in the second iteration here, I'm going to say while the second parameter, while the second joint angle, let's see, what do you think is less than 135 degrees? And then I need to make sure that I'm adjusting the second joint parameter. So, oh, that was because I should probably do one of the subsequent joints now. That's not really nice. So, how about, let's see, we have the -60, yeah, over, say, 3, and we'll say that that one is less than +60. So what this will do is it'll actually elevate that second joint after we get done with the first motion. Just like that. And so we're almost to the point now where we're going through and can start modeling the motion of our robot. I'll do it again because it's kind of cool. We could do something like this so it's waving at people. It'd be kind of tedious, but. Okay, so does this kind of help you start to put stuff together as to what we're doing with this? Because now that we have the basic setup for, I mean, this is the heart of our forward kinematics. Now that we have this available, we can really start to model motion within our workspace. All we have to do is go through and use these transformations in order to perform each of our subsequent motions. Good. Okay, so since we're